Okay, so hi, my name is Maciej Dziubiński. I work as a machine learning engineer at a company that specializes in fraud detection. It doesn't specialize in self-driving cars whatsoever. So this is a hobby of mine. And I should say I finished the Udacity course about which Carolina was talking about, and I finished the version with 3 terms, and yeah, so there was a bit more content, but from what I saw, it's still a pretty good course, and personally I can recommend it, although I know it's a bit costly. Okay, so the topic of this presentation will be developing a testing environment in the CARLA simulator, and I added a WIP, which means work in progress, because I was hoping to show something more, but it turns out that the clash between reality and simulation is harsh. So you'll see what I managed to do, and I'll say a few words about what I'm planning to do. Okay, so the agenda. I haven't added the third point. So anyway, along with Karol and another friend of ours, Łukasz, we started this idea that we can take part in this competition called F1/10th competition. I'll show a video later on. And the competition took place in October. We actually won the competition. We had a small car in 1/10 scale, which is in size similar to that one, although it had different sensors. And after the competition, I talked with the organizers, why is everybody using LiDARs? Because everybody uses LiDARs, like, the default sensor was a LiDAR. Why didn't anybody try deep learning? And they said that they did try deep learning, but it doesn't really work. So I thought to myself, well, come on, you're doing it wrong. You have to be mistaken. So I thought to myself, well, I'll try to take part in the next competition, perhaps not necessarily to win, but just manage to drive the car around the track with a deep learning approach. And I figured that the best way of doing that is by using transfer learning from a simulation, so that I'll teach a car to drive around the simulation, and then it will be easy to transfer that knowledge into reality. Yeah, so the next competition is in April. We'll see how it goes, but so far it's pretty harsh. And okay, so then the idea was to use a simulator. So I checked out all those open source simulators that Adam was talking about. I can add to that stack AutoWare, which is in a gazebo environment. And I got a bit late for the presentation, and I've managed to hear Adam. Adam, yes, say a few words about that. The open source simulation world is a bog through which we have to, I don't know, go through or something like that.
Not that bad, but you need a lot of work.
Yeah.
Anyway, right?
Yeah.
When it comes to open source solutions,
you need something that works.
But then, in this case, you have to work a lot.
Yeah, and this morning I came to work with my car. I usually don't drive a car to my work, and in the morning it was freezing, and I actually parked in a bog, and it was fine because everything was frozen, and my shoes are ruined now, and they're all in the bog. So yeah, I went through the simulation world. I wanted to choose one particular simulator in which I could train those neural networks. And I stuck with CARLA, mainly because, well, there are 3 reasons. One reason is that they do provide some software, open software, so for testing out, the most primitive models. So there is imitation learning, which is also called, I think, chauffeur learning, where you have It's something like that. So imitation learning is like behavioral cloning with instructions from a person that knows which way should the turn go right now. And there is also a package, there is also a repo for reinforcement learning. If somebody's interested in that, I can share the links. Yeah, so I stuck with CARLA. maybe I'll start the presentation, okay? So the F110 competition. Here's a promo video from the competition, from the October competition. There is no sound, but it's not that important. So yeah. So the competition took part in Torino, which is in Italy. Okay, so my comments are not that necessary, but there were 9 teams from all around the world, from Korea, from US, from Czech Republic. There were 2 teams from Poland. I probably skipped from Italy and from other countries. So here are the organizers. And I think that what's important is that the track, you don't know the track beforehand. Before the competition, you just arrive and then you see how the track looks like. And it's the track is ideal for a LiDAR because that was our car, by the way. But anyway, so the track is ideal for a LiDAR. There are no reflexive surfaces besides the floor. Everything is smooth, everything is flat, it all works out perfectly, and our approach was pretty simple. It was a sort of an algorithm called follow the gap, meaning that from all the LiDAR points, you determine where the gap is, or where you can go, and you just go that way. And it's pretty fast. It doesn't use localization, it doesn't use mapping, it's very, very simple. At least in terms where you have to go. The tricky part is how fast you have to go. So this should load, and this is actually our attempt. So the competition was to drive as many laps as you can in a limited time. So the first session was 5 minutes, then the second session was 3 minutes. So we managed to make, I think, 18 laps in the first run, and then 11 or something like that in the second. So this is how the car goes. And actually it accelerates because there is open space. Then there is a very tight turn to the left. And then there is a very long straight where the car really accelerated. You can see that it's oscillating, technical details. I'm not going to go into that. So yeah. Oh, how can I go? All right. So here's a video presenting the CARLA simulator. So it's a marketing video. Everything looks nice. You have changing weather conditions. The graphics are pretty good because this is an Unreal 4 gaming engine. Besides RGB, you get semantic segmentation, and also a depth map. This is the depth map, meaning that the further something is, the wider it is. And that'll be crucial for the rest of the presentation. So yeah, so CARLA is pretty nice. The main reason why I chose CARLA actually was that the community was thriving. It was very easy to get an answer to a question. They have a Discord channel. It's very lively. People there are very nice, and that's a big plus for me. So yeah, that was a very important factor. The second important factor was that it was in Unreal 4, meaning the gaming engine, because in gaming engines you have to write in let's say low-level code, so that was C++. It so happens that I know C++, so I felt very comfortable with that. Unity is C# mainly. I don't know C#, so that was a factor. And the third reason was, is there a question? No? No. And the third reason was actually that, from what I gathered, it's easy to create your own maps in CARLA. So that's what I did. I created a map that would more or less resemble the racing conditions in the competition, meaning that I have a racetrack which is bound from both sides. And this run is actually, this is a neural network controlling the car, and it's controlling both actuators, meaning steering and throttle. This turn is pretty tricky because it's very wide. Here we have a chicane. The car decelerates in the tighter turn, then it accelerates. You can see the speed here. I know that you might not see it very well from afar, but what's important is that the car manages to speed up on straights and slow down in those turns that are too narrow for the car to be able to get through. So this is an example, I think. So it really slowed down in order to avoid collision with the barrier. That was pretty awesome. So I used a convolutional neural network, but I used as input the depth map. So the information about how far things are. There was also a second reason why I used a depth map, because I knew that there are so-called stereo cameras. I have 2 of those stereo cameras in my car. So I figured that if I can train a neural network in the simulator on the depth map, it would be easier to transfer that knowledge into reality, so that when I have a neural network that's operating on depth maps in the simulator, I'll be able to, use that neural network in reality. Maybe I'll leave the details about how the architecture looks like. I've written a blog post about building the racetrack and how I trained the neural network. Oh, come on. Here's the link if you want to follow it. So leaving out the technical details for maybe discussions later, let's skip straight into the stereo cameras. So one approach to stereo cameras is that you have an image, or rather, you have 2 images coming from 2 lenses that are separated by a baseline. And what you do is you combine those 2 images and you try to infer the distance of those objects. And here is a simple object. There are 2 images, and this is a very, very simple script that combines the information and tries to infer the distance. So as you can see, it doesn't work very well. The reason is that this is actually coming from those 2 lenses here. They are not very far apart, and also the script that was used here is very, very crude. And there are better techniques. One is to project a pattern onto the object, and this projection allows for better matching of those 2 objects, or rather those 2 images, and better inference of the depth. So this camera actually does that. It has a projection, it has a projector rather, an IR projector, which allows for a better depth recognition, and the image on the right is actually using the image on the right, the depth map on the right is actually using those patterns, and the image on the left is using a better script than the previous one, but without the patterns. So you get a significant increase in the quality of the image. And here is the camera, and here is the output from or rather the depth map from it's called Intel D435 camera. That's the one I have. So it looks pretty good. But the reason why it looks pretty good is because people are very good at discerning colors. If this image was black and white, it wouldn't look as good. Black and white is less, we are less susceptible to black and white. So what I'll show you next are images that are black and white, and they look very, very poorly. The quality looks very, very low. And this is because our perception is, modeled for color images. So on the left is one example. This is actually my office where I work. So one problem that you can see is that the surface is reflexive. So it sort of fools the camera. There's also a second problem, this one. I don't know if you've noticed, it's becoming darker. This is because the auto exposure is on in the camera. So there are some problems which I was facing. But you know, I thought to myself, well, the information is there. I just have to extract it. It's nothing hard. So here you can see the reflexive surface. This is the second run. I actually used the second run as a test set for my neural networks. This is actually my house. So it's a one turn in my house, because before this presentation I got sick and I wasn't able to get out of my house, so I had to drive around my house to gather data. The quality is a bit better because I've tried to work with the auto exposure, but as you can see, it's still pretty rough. So my first intuition was to you know, remove all that noise that you can see here, because in the CARLA simulator, one thing is for sure, you're not getting any noise. So that was something that I needed to tackle. And I used denoising autoencoders. I used various algorithms in the OpenCV library. I tried, at one point I tried generative adversarial networks, which Adam mentioned. They didn't work very well, but I suppose that they can work for something a bit different. I'll mention that later. But it turned out that the best solution, or rather the best results that I got, were for a very simple algorithm that you know, goes with a filter around the image and just extracts the maximum of the pixels that are in that filter. So on the left you have the raw depth map, and you've seen that before. And on the right you have the smooth version. As you can see, it looks very blurry. Surprisingly, you get better results for the blurry version than, or maybe not surprisingly, you get better results for the blurry version than for the rough raw version. And this is how the depth map looks in the CARLA simulator. To be honest, it's not that good. The quality is very low. If I were to drive around this track with this sort of input, I would struggle. So I figured that because this input is very rough, I'll be able to train the neural network, because both the reality and the simulator look rough. But on the other hand, there is no noise in the simulator. And it is a bit different, right? There is this, there is a huge difference between those two worlds. So what I tried first was, just one important note. This is how the scatter plot of steering angles, where on the x-axis you have the actual steering angle, and the y-axis you have the prediction for both train and test set. On the left you have that was actually my first attempt of building a neural network in CARLA, and on the right you have the result for the red Audi that you saw in the video previously, where I said that there is a neural network trained to model the throttle and steering. So this is the output for that. So you get a correlation on training set 0.98. I know that it might be hard to see, and on the test set you get a correlation of 0.95. Actually, if you get a correlation of 0.8, the car will be able to get around the track. So that's my experience. Okay. So this is how the correlation plot looks like when I use simulation and real data. Obviously, I used standardizing techniques. I tried to make the gap between reality and simulation as small as possible, but still, the correlation on the test is 0.53. That's not very good. That's actually very bad. 0.53 is, in the simulator, you can get that from, like, let's say, 1,000 images. So, no, even less. I think 500 images, you can get this sort of result. But what's optimistic, or two optimistic things. One is that it's actually able to, the model is actually able to discern whether this turn is left or right, more or less, I mean the mean. And the second thing is this narrow, there is no way I'm gonna use the touchpad like that, this huge weird predictions. So for the truth being that goes straight, the model predicts everything between -2 and 1 and 2, meaning that there is something called state aliasing. So from the perspective of the model, there is no difference between two frames where one frame goes straight and another go left or right. State aliasing is actually a big problem with behavioral cloning, and it so happens that I have some techniques to manage that problem. So that's pretty okay for me. But still, the problem here is that there is some information, but it's too hard to extract using the neural network. My second approach was to use transfer learning, and I got a slightly better. The quality is very low, but I got a slightly better correlation of 0.56. That's not a huge improvement. And the neural network that I used was actually a neural network that was able to drive the car and the simulator very, very well. So I got the right features, or rather, I thought that I had the right features, meaning that the neural network was able to, the convolutions were able to find relevant features in the depth map. And I thought to myself that, well, there might be two discrepancies. There are discrepancies in the input, and there are also discrepancies in the output, meaning that the steering angle in the reality, so a value of 2, means a very different thing than a 2 in the simulator. So I had to account for that. And my reasoning was that the transfer learning technique does account for that, because what I use is I extract the first layers of the neural network, the convolution layers, and on top of that, I stack the layers that are going to be trained on the real data. So yeah, and the output was actually the one that was in the reality. So I was hoping that if I have the right features, I'll be able to, let's say, transfer the knowledge or train the neural network so that it can, map or rather predict the steering angle in reality. That didn't happen. I've spent a lot of time debugging those two approaches, and I didn't find the bug. It's just, I think, there's this so-called reality gap, so that simulations are doomed to succeed, meaning that it's very easy to train a neural network in a simulation that works. It's a very different story to do the same trick in reality, or to transfer that knowledge from reality or rather from simulation to reality. So, it so happens that it sort of aligns with my interests, machine learning interests, mainly domain adaptation, because we use domain adaptation in my work, where we have different domains, meaning that we have different data sets on which the distributions of features are very different and the output is very different. But we know that the knowledge hidden in those domains is the same, or rather, there is this assumption that there is the same information in those two domains. So, because I had some experience with domain adaptation, I thought to myself, well, it shouldn't be that hard. It should be actually, there has to be some publications or some attempts of doing that. And one of those publications, or rather the one that I know that works, is the unsupervised domain adaptation by backpropagation. This is a very simple but efficient trick where you have the standard output, let's say that this is the steering angle, of the car. But you build also a different and auxiliary output, which is supposed to predict the domain. So what the neural network would normally train, or rather what would the neural network normally learn, are features that help the neural network discern between domains and also model the steering angle. But here there is a twist. The gradient coming from the bottom red neural network gets its sign reversed, meaning that when you update in backpropagation, when you update the weights, the updates that come from the lower part of the neural network, they increase the weights, which means that the neural network, the weights are updated in such a way that the neural network has a harder time discerning the domains, which means that it has to learn features that are common to both domains. It has to find features that are, that can be used in both domains, because it doesn't know how to discern between those two domains. This is a pretty awesome trick. There are various implementations of this because it's pretty easy to write in TensorFlow or PyTorch or whatever. The harder part is when you have multiple domains and you want to transfer knowledge into a common latent space. That's where generative adversarial networks are more valuable and variational autoencoders come to play. So the second paper that I found interesting, and I haven't tried it. The previous one I tried and I know that it works. This is from a company, I think, or a startup called Wave. This is a paper from December 2018, which Carl posted on the, yes, Carl did, posted on the, on this meetup Slack. You can join the Slack, there are very valuable links there. And the idea here is to find a latent space, so this is this part, and you have the input from simulation and you have input from reality. Well, what you learn is you learn how to transfer the input into the latent space, then from the latent space into reality, then go back to the latent space, then to the simulation, etc., etc. And you have multiple losses that account for that. So you have losses that account for transferring from simulation to latent space, then to reality, and the other way around. And there are multiple combinations of doing that. And all those losses, they all have their own contributions. And there's also a variational autoencoder involved. So you have generative adversarial networks and variational autoencoders. So at first I thought that this paper is, it's very interesting. But what it turned out that it's pretty, you get the impression that they did all those things that people already did, but on a larger scale. They actually use their own simulator, they generate their own tracks, and they use it in reality. But in truth, most of the things that they did were actually done before that.
Excuse me. Okay, try to continue with the...
Okay. So here's an example. The image from the bottom comes from the unsupervised image-to-image translation networks from NVIDIA. Here's a free open source implementation. Oh, because I forgot to say that the paper from Wave doesn't have an open source implementation. Also, the paper is more like a marketing paper. It's a white paper where you don't get all the details that you need to reproduce the work, in my opinion, at least. There are some decisions that I find, well, they use, for example, LS GANs. Why do they use LS GANs? Why not different GANs, etc., etc.? So there are these three different questions that pop up when you read the paper and you don't get the answers. Well, you get the answers in different papers that are on which this paper builds, and one of those papers is the one that I mentioned, and try to spot 10 differences between the image on the bottom and the image on the top, without knowing what those things are. I mean, this is very similar. I know that the idea or the execution becomes, more concrete in the Wave paper, but still, you can get more details and you get open source implementations elsewhere. So it's a very big paper in terms of what they did, but it's not that good if you want to reproduce their work. Also, what they cite, because it's not that they don't cite those papers, they do, but it's not a problem. I also cite a paper from 2017, I believe, Real Virtual Domain Unification for End-to-End Autonomous Driving, where they do pretty much the same thing, but they don't have the reality. They didn't have the money to reproduce that in reality. So it's sort of a cheap approach, which is good for me because I'm cheap. I have to do it cheaply. I don't have a real car. I won't be able to drive a real car. And this is another approach. It's also using GANs. And there is a recurring pattern between those papers. There are multiple papers like this. But there is a recurring theme, or rather two recurring themes. One is that you have to cycle, you have to have a loss for recreating the input image. So once you get, you move the image to the latent space, you have to be able to go back. So you have a loss in all those approaches that I found. You have to have this cycle relation and cycle loss for recreating something that you move to the latent
working space. There's this one pattern, and the second pattern is that you have to supply the neural network with additional information. In this case, we have image segmentation. So image segmentation is something that's being optimized as well during training the neural network. And I thought that maybe Carl will be interested in this because I know he uses image segmentation for driving a racetrack, so maybe he'll be interested in this paper, especially because there is an open source. So there are two recurring themes. You have to have a cycle loss that accounts for the fact that once you move to the latent space, you have to be able to recreate what you moved. And there's a second part, you have to supply information, because supply additional information. Because if I used this sort of approach for or rather, if I used a general adversarial networks for my noisy images from the depth camera, and I would hope that it would generate the images that are resembling the ones that I had in the simulation, no way is that going to work, because I don't supply any additional information. Neural networks are not magic boxes. They don't produce new information. They just extract very entangled, very difficult to find information within the data. So yeah, to close, thank you for your attention. It's not the end. It's not the end. So to close, what I have to do with my car, now I know that transfer learning doesn't work. Now I know that the reality gap is real. What I need to do is supply my approach with this method of domain adaptation, or rather, getting the data into a common denominator from which I'll be able to model both the simulation and the real reality. And just to close, I had one more idea, because there was Blender mentioned. Before I tried the transfer learning and I knew that it doesn't work, etc., I thought to myself, well, I can become a master of Blender and Unreal Engine 4, and once I get to the competition, F1 competition, I can remodel the map in Unreal, then train a car in this map, then transfer that to reality, and maybe that will work. Of course it wouldn't, but in my head that was a brilliant idea at the moment. But it turns out that NVIDIA did something like that, or although much better. This is also a second link from Carl from the Slack, so try to join it. So join. Here's an approach from NVIDIA where they use HD maps to move the data into Unreal Engine 4 and drive around in a simulator, crashing people in another car. So this is a simulation. So happens Unreal Engine 4. They use Unreal Engine 4 to move the point clouds into the simulator, which is awesome. I think that's awesome. So this is how it looks like. It looks very well, very good, because this is a marketing video. This is my idea, to use Blender, to be a master of Blender, and to use it in a racing competition. This code is like so marketing. You can get more marketing. Anyway, so you can model the cameras and stuff like that. Everything works. Everything is pretty. I bet it's not open source, etc., etc. This is how it looks like in reality. You get a traffic jam because of the data collection. Yeah, so it looks very nice. And then I stumbled upon a project in the library for the, I cannot click, come on. I'll use this link no matter what. There's this wrapper for the Unreal, for the camera. It's called Unreal Engine 4 wrapper for RealSense. RealSense is the name of the camera, SDK 2.0. Where you transfer the point cloud into Unreal Engine 4, and hopefully everything works out, and you can model the racing conditions in the content competition and train the neural network this way without becoming the master of Blender. Again, I know this is very naive, I know that it doesn't work like that, but still, it might be, it's an interesting angle, it's an interesting idea for a hobby. So yeah, thank you very much for your attention, and let's have one or two short questions. Oh, sorry.
Just one question. Did you pay some, let's say, attention to sensor simulation, like noise simulation itself?
Sensor simulation?
Yes.
What does it mean?
Did you try to simulate the noise of the sensor?
In the simulator?
Yes.
I thought about that, but the reflections on the surface, I'm not sure if that, you know, there's one problem, how do I simulate the reflections? And depending on how I do it, it's either going to work or it's going to fail miserably. Yeah, so I thought, nah, I'll try to do something else. But I am open to suggestions.
I mean, one big problem of all simulators is that they're not paying enough attention to
Noise.
set noise in the sensors.
But how can I model that noise?
It's extremely difficult, to be honest, depending on the sensor. But you can try to play with the abstraction of the noise from the, you know, trying to compare the real world versus what the sensor readings you have, and then try to make a map of the differences between the two worlds, and then try to play with it. It's just one of the easiest ideas.
It's like a down or something.
But basically, it's really challenging. I mean, from our perspective, we worked on this with LiDAR data, and you have teams of 20-30 people just trying to simulate noise in LiDAR. It's super difficult.
I'm guessing it's not open source.
No, it's not.
Any other questions?
Okay. So.